first postdoc? I'm sorry.
Yeah, first postdoc.
And is a postdoc at Princeton University. So he's worked on black holes, cosmology, and most recently the connection between space-time locality and quantum information, and the blue box, to which you were not supposed to pay any attention.
Yeah, this is an interesting...
There's some sort of glitch here, so please don't ask any questions or make any jokes about the blue box. So without any further ado, Daniel Harlow.
Okay, thanks for the invitation. It's great to be back at Davis. Fun to be talking to a broad audience. I guess the last time I was here, I was over in the math department, and I was talking about p-adic numbers. So I'm going to use that as an excuse to this time talk more about physics. There will be some dimensional analysis and that sort of thing, and I hope the mathematicians will forgive me. And I should say also that please ask questions throughout the talk. I'm going to be building on a bunch of things which aren't all familiar to everyone, and I'm going to try and be reasonably self-contained. And things are designed so that if you stop me and I don't quite get to the end, that's okay. We'll still have gotten at least to some of the important things. So it's much more fun if we stay engaged. All right, so I'll just start a little bit by talking about the big picture. So what do? I try and understand quantum gravity. People have been working on that for a while, including some pretty smart people. And they haven't solved it yet. Why haven't they solved it yet? Well, so I guess this is tolerable, I suppose. People give various reasons for why quantum gravity is hard. For my money, the real reason is because gravity is a universal force. Everything couples to gravity. And what that means is that it's very hard to operationally define observables in quantum gravity that you really expect to be completely precisely well defined. And the reason is that if you want to locally probe things at the Planck scale in a physical way, then you have to say where things are at distances of order the Planck scale in a physical way. So if you like, you need rods and clocks, right? Rods and clocks are how you make relativity operational. But here there's a problem, right? Because here we have both G and H bar. We're doing quantum gravity. And since we have H bar, we have to deal with the uncertainty principle. So we have to localize the rods despite the uncertainty principle. But then because we have gravity, we have G, then the rods are self-gravitating and they can collapse to form a black hole. And I emphasize that that's because of the universal nature of gravity. If there was stuff that didn't couple to gravity, then we would just make the rods and the clocks out of that stuff. And then we would be able to have precisely defined local observables. Now, to emphasize this, I'm actually going to make this argument quantitatively for you. So here's some idealized collection of rods. You should think of it as three-dimensional, although I only drew 2 dimensions of it. And on a side, it'll have size capital L, but then the spacing of the individual rods will be of order the Planck scale. So this is the kind of thing I would need if I wanted to talk about a precisely defined local observable in the quantum gravity theory, at the scales where quantum gravity is important. Now, this collection of rods, I'm going to try and make it satisfy the 2 constraints I said before. So the first one is I don't want it to be a black hole. If I don't want it to be a black hole, then I need the linear size, L, to be large compared to the Schwarzschild radius of this collection of rods. So that's G times M. So here, I guess, I'm always working in civilized units where C and H bar are 1. And actually, I guess I'm also working in string theorist units where 2 and pi and that sort of thing are also equal to 1. So G is L Planck squared. So the mass is just the number of rods, right? So that's L over L Planck cubed. That's just the volume in lattice units. Then the mass is the mass per rod times the number of rods. And then there's an L Planck squared here, but I moved an M Planck down there so that the units match more clearly on the 2 sides. Now, okay, given this inequality here, then the obvious thing to do is to move the L Planck over here and then cancel an L over L Planck from both sides. Moreover, since I want the collection of rods to be big enough, to have multiple notches on the ruler, I want this ratio, L over L Planck, to be big. And then you see the only way I'm going to be able to satisfy that is if the mass of each individual rod is small in Planck units. Okay? That's what I need to avoid making a black hole. Now, the other thing I need, though, is this thing I said about the uncertainty principle. So I want the rods to be localized. Can everyone see the bottom here? Is my computer blocking? Try and I don't know if that makes it worse or better. So I want the delta x of each individual rod to be small compared to the Planck scale, so that the rulers are well defined. Now, we all know that the uncertainty principle says that delta x has to be greater than 1 over delta p, and since I'm interested in the situation where the rods aren't moving very fast, I can use the non-relativistic formula p equals m times v, so it's m times delta v. Now, moreover, since c is 1, and I don't want the rods to be flying around at the speed of light, I want delta v to be small compared to 1, which means that this thing is bigger than this thing, okay? And now if you just look at the chain of inequalities, right, this, and remember L Planck is 1 over m Planck, then this tells you that the mass per rod has to be large in Planck units, okay? So obviously there's a tension between these two things, and I will claim that this is why quantum gravity is hard. This is why we still haven't solved it 60 years later. Now, sometimes people will tell you that it has something to do with non-renormalizability. This is false. Pions are also non-renormalizable, and we understand them just fine, okay? This is the thing about gravity that's hard. Now, I should emphasize this is a theoretical problem. The issue is that a theory of quantum gravity shouldn't be able to precisely answer the types of questions that we usually ask physical theories to answer, the ordinary quantum field theories that we talk about in day-to-day physics. In a quantum field theory, the kind of question you like to ask is, if I do this here, what happens there? More formally, things like correlation functions of local gauge invariant operators. I claim that that kind of thing is not a thing that should make sense in quantum gravity for the reason I just said. Now, there's also a practical problem, nicely boxed, that L Planck is small compared to L person, which makes it hard to do experiments on this scale anyway, okay, as I'm sure all the experimentalists have already been thinking for the last 5 minutes. I'll comment on this in a sec, but my focus today is the theoretical problem. Okay. Now, in fact, there are theories of quantum gravity that have been discovered in the last 20 years, good, nice theories of quantum gravity. But what always happens is that in these theories of quantum gravity, you don't get to ask the kinds of questions I just described. The things that are naturally described are scattering experiments, where, so here's some representation of space-time, where time is going up and space is going this way. Light is moving on 45-degree lines. So this is often called a conformal diagram or a Penrose diagram. So you send in some stuff from t equals minus infinity. Something happens in the middle. You don't really worry too much about what it is. And then something comes out. And then you just ask about the amplitude of the in to the out. And you only ask for that to be computed by a theory of quantum gravity. So then the nice thing is that because, when you're interacting with the parts of the system, they're sort of asymptotically far away from each other, you can carefully prepare and measure them without disrupting what's going on in this region here where quantum gravity is important. So you might take a sort of extremist view and say that these are the only types of things that quantum gravity should ever talk about. This is a viewpoint that one often encounters. Certainly saying that these are the only kinds of things that you should expect to be completely mathematically well-defined in a theory of quantum gravity is something that I'm sympathetic to. I'm not sympathetic, however, to the point of view that this is all we should ever talk about. And there are some very empirical reasons why we can't just be satisfied with that. So reason number one is that we don't live at infinity. We live in the middle of the universe. We're not out in any infinity. We're doing our experiments right here. The universe is undergoing, we think, a period of rapid exponential expansion. There was inflation in the past, at least most of us are reasonably confident. And there's also a cosmological constant today. This is by now there's incredibly compelling evidence for this. Now, I guess for any cosmologist here, I'm sorry, this is the 2013 Planck data and not the 2015 Planck data. I've been traveling and I didn't have time to figure out how to open the new file format. But this is amazing, right? I mean, this is an incredible agreement of theory and experiment in a situation where we're not staying out of infinity and we're talking about things right in the center. I mean, this is a 6-parameter curve here, this red curve, it's lambda CDM. And the fact that it fits all of these data points is really a remarkable scientific accomplishment. And so we've got to be able to, do this calculation in a theory of quantum gravity. And I should emphasize that in this kind of universe, there's really no asymptopia for us to run off to. I mean, this is us up here in de Sitter space, and we try and separate our experiments. So maybe I want to do a scattering experiment. So, so I keep separating my guys, and then suddenly, oh, oops, they fell out through the cosmological horizon, and now I'm never going to see them again. So that's a very, very fundamental thing preventing you from doing a scattering experiment in this kind of scenario. So this green region here, really down to the corner here, is all that's accessible to us, even if we wait for arbitrarily long times. So everything we see is really just confined within a finite volume, about 10 gigaparsecs across. So I think we really have no choice except to try and make sense of experiments done by people who are limited in sort of how far they can separate things. So that was empirical reason number one. So empirical reason number two is that there are black holes. So this is a nice picture of a black hole. I guess it comes from the movie Interstellar. I guess this thing here is a habitable planet, which is supposed to be orbiting this supermassive black hole. I guess I'm not really sure how that got there. I mean, probably I guess if you ask an astrophysicist, they won't expect you to have habitable planets sitting around this close to Sagittarius A, for example.
No, Kip Thorne worked it all out very carefully. No, it's not physically impossible.
Right. It's all just very improbable. Yeah, exactly. Right. Now, which actually, from a dramatic point of view, is incorrect. If you read Aristotle, what he tells you is that the audience will easily accept the impossible, but not the improbable.
That's right.
So I'm not as good of an artist as Kip Thorne. So when I draw a black hole, it looks like this. So this red thing up here is the singularity, and this dashed line is the horizon here. This orange line is the matter I use to make the black hole. And this blue line is some observer who's going to jump into the black hole, who I guess conventionally is called Alice. But I feel bad for Alice because she's always getting thrown into black holes. But the point here is that if you think about the experiments that Alice does, right? Out here, what she does is basically a scattering experiment, right? Alice is one of the ingoing parts of the S matrix, along, with her lab and whatever. And she does some experiments here, and then she sends some results out to infinity, and they get published in PRD or whatever. But when she crosses the horizons, she can't send her experimental results out anymore, right? Because you see, remember on these pictures, light moves on 45-degree lines. So this part of the blue line up here behind the horizon, no matter what message she sends, it's going to end up in the singularity. Which means that describing Alice's observations is not a scattering experiment. So, yeah. Where does she go? Well, she just dies, but she should see something. So, unlike the cosmology example I gave, this is not an experiment that we actually do. I don't get to show you a plot like the plot I showed for the previous one. Nor is it an experiment that we're going to do anytime soon. But nonetheless, I still think it's an important question to think about for several reasons. So One is that, well, it's an experiment that could be done. So, if somebody comes to you on the street and they say, I've got a theory of quantum gravity, you should ask them this question and see what their theory says. If it's a self-respecting theory of quantum gravity, well, it should either give an answer for what happens to this thing that we imagine we could actually do if we had a black hole, or it should somehow explain to us why that's a stupid question and we were all being a bunch of dummies for being confused about it. So that's the sort of principled answer. Now, I should also say, though, that it's a more tractable problem, or at least it seems to me to be a more tractable one than the cosmological version, because Alice, at least half of her experiment is a scattering experiment. We can prepare her at past infinity, and even though her results can't get out to future infinity, the Hawking radiation can, the various other parts of the system can, so at least somebody gets to do scattering experiments in this setting. Okay, at least somebody does. So in that sense, it at least seems a little more easy to get your head around than these cosmological things where you're part of the universe and everyone else is too, and no one is a sort of privileged observer. Okay, and now finally, so I promised I would only say this word once. So these guys, this is Almiri, Merrill, Polchinski, and Sully, argued that recently, well, not that recently, maybe 2.5 years, almost 3 years ago now, that the consistency of quantum gravity actually requires the horizon to be singular, which is what they call a firewall. And so remember, the horizon was this point here, where from the point of view of general relativity, solving Einstein's equations, there's nothing locally special about the horizon. You just fall through and you don't even notice if the black hole is big enough. So if this is right, if these guys are actually correct, this is a big blow, right? This is saying that, effective field theory, the thing that we base all of our current understanding of the universe on, is wrong. And it's wrong in a different place than where we are used to it being wrong. And in particular, it's wrong for exactly the same kind of calculation that goes into making this curve. Okay? So if you really think that there's a firewall, then you should probably be skeptical of this. You should say, this red curve is not really, this is just based on doing the same kind of quantum field theory and curved spacetime calculations, in a very similar setting mathematically, to saying that the horizon is smooth. Now, obviously here, the agreement, this is real data here, right? So this calculation is not wrong, okay? But that means that we don't really understand it well enough, right? It means that, then we would have to understand why it's correct here and why it's not correct in the other case. And that would require some new kind of theory of physics. And certainly for me, probably it'd be simpler if it's right here and it's also right for the black hole and actually there's no firewall. I guess that's probably where my money would be. But we need to understand that. The arguments these people raise are serious arguments and they can't just be dismissed out of hand. Okay. So I think that learning how to describe Alice's experiences in a theory of quantum gravity will teach us important lessons for cosmology. And not just in terms of justifying the theoretical calculations we already know how to do in cosmology, but also in addressing observations in cosmology which we currently aren't able to explain in a satisfactory way. Things like why is the cosmological constant so small? Why are the parameters of lambda CDM what they are? These are the kind of questions which can't be answered in effective field theory, but I think there's reasonably plausible arguments that they can be answered in quantum gravity. But to do that, I think we're going to first have to solve the black hole problem. Now, when I was a graduate student, I spent a lot of time working on the cosmology problem, and that was hard. So, as a postdoc, for a while I've been working on the black holes, retreating to something a little bit more well-controlled. And in fact, today I'm going to retreat even further. So even the black holes are a little bit hard. So today, I'm going to talk about a set of questions similar to the things I've been discussing here, but in an even more controlled setting, where I actually understand things well enough that I hope I can convince you that I can resolve the problems instead of just being confused. Yes?
So before I change the question, on the question about Alice's Are you saying that we should be able to answer questions about what we see as observers outside the black hole, or what Alice experiences, but we will in fact never know?
Well, but we could be Alice. We could be Alice.
So that's what I'm asking.
Yeah, so no, it's Alice that I'm worried about. Yeah, it's Alice that I'm worried about. From the outside, I don't really see any serious problems. I mean, there is of course the question of whether or not black hole evaporation is unitary, which is a question that you can test from the outside. But for my money, that one's already been settled and it's unitary.
For that, your money what?
For my money, that one has, at least I wouldn't say been totally convincingly settled, but I would say the evidence is very strong that it's unitary. Yeah.
How's black hole evaporation represented on your diagram?
Oh, in the Penrose diagram I drew? Yeah, so that's this thing up here.
Just the edge.
Yeah, it's this edge. So if it hadn't evaporated, this line would have gone down like that. And there wouldn't have been this extra vertical line here. So that's saying that if you wait long enough, so this line here is the origin of polar coordinates. It's r equals 0, and so is this line up here. So the Hawking radiation is sort of coming out here, and at some point it's all gone, and then it's just back to Minkowski space at the top. Yeah.
How many people feel convinced by this AMPS paper?
Well, what does convinced mean? I mean, I'm not convinced.
That's just you,
No,
but I kind of guessed that.
No, I don't
And
think,
that's good. But
I don't think convinced is a strong word. I don't think anyone is convinced. I mean, I think people are convinced that we don't understand how to think about the interior. I think the paper convinced most people of that. Now,
Okay.
that's different than convincing us that there are firewalls. I think not many people would be convinced there are firewalls, but at least many people are convinced that we're confused.
I don't think that amps are convinced that they're a fire.
No, they're not either. Yeah, no, they're just saying that there was a naive way of trying to think about it, which they said is wrong. Yeah, there was a set of words that sometimes go by the name of black hole complementarity, which people used to say to make themselves feel better about the infalling experience, the experience of the infalling observer being smooth and the information getting out. And AMPS argued in a sort of clear way that that set of words is not internally consistent.
I see.
But I mean, the AMPS was just the beginning. I mean, there have been more papers since then, and I think the real lesson here is that we don't know how to describe the interior in something like ADS-CFT. I mean, I think that everyone agrees on. So that's what we need to figure out.
So firewalls, doesn't really have the status of a solution. It's just some sort of...
No, absolutely not. No, I mean, a firewall the firewall argument is a negative argument. It says that some collection of ideas can't all be true, but it's not a positive argument in the sense that they never gave a theory of the firewall or how it forms or any of that.
Okay.
And they would be the first to admit that.
Okay, well that's a relief.
Yeah. So sorry, I have a sore throat, so I'm just getting a cough drop. My apologies. Any other question?
No.
Okay. So okay, anytime we have a hard problem, okay, as you all know, what we need to do is find some toy model that captures some aspects of the physics, but that we can actually study and learn about. And this is strategy number 1 in the How to Be a Theoretical Physics textbook. So, and in fact, for the rest of this talk, I'm not going to talk about cosmology at all. And I'll talk about black holes at the end, but even that, not very much. So what I'm going to do instead is focus on this question. So in a certain kind of quantum gravity theory, ADS-CFT, that we understand fairly well, which does have a nice asymptotic region for scattering, I'm going to ask, can we talk about the stuff that's going on in that question mark that I drew before? Although the theory likes to talk about it from the point of view of the scattering, I send stuff in and I see what comes out. Can I stick its feet to the fire? Can I say no? I don't want to wait until the stuff comes back out in infinity to know what happened. I want a computation I can do right in the thick of things, and still see what's going on. And I think clearly, if we can understand that, that's already helping us overcome our unhealthy addiction to living at asymptotic infinity. So the theory I'll use is ADS-CFT, proposed by Harlow in 1998. So I guess some people in the audience are very familiar with this. Some people are very unfamiliar with this. I'm going to try and be self-contained about it. So I'm not going to assume you know anything about it. So Huang's proposal is that quantum gravity in asymptotically anti-de Sitter space, ADS for short, should be defined or most precisely understood as a quantum field theory with no gravity, in a lower number of space-time dimensions. And I'll say more about what these things are in the next slide or two. Moreover, the quantum field theory has a special symmetry, conformal symmetry. So it's a conformal field theory. That's the CFT. So here's ADS and here's CFT. And in fact, in string theory, Huang did more than just suggest this. He gave an explicit example where you could essentially derive this, and where you know what CFT you're talking about, and you roughly know what quantum gravity you're talking about, and where you can compute things on either side and check. And so since then, other examples have come out too. Now, just maybe for the people who don't follow this stuff too much, I should emphasize, or maybe tell you, this is the most cited paper in the history of theoretical physics. I'm not kidding. It's more cited than BCS. It's more cited than anything written by Phil Anderson, more cited than the Standard Model. You can decide whether that's a good thing or a bad thing. I'm not going to pass judgment. I'm just trying to emphasize how influential this idea has been. I mean, not just for thinking about quantum gravity. That's what I'm doing today. But it's been influential for many other things too, in mathematics, even in quantum field theory, just studying quantum field theory, even studying condensed matter physics. So good. So now let's just try and understand a little bit more what the two sides mean. So asymptotically ADS. Well, first we have to understand what ADS is. So anti-de Sitter space is some solution of Einstein's equation. It's the maximally symmetric solution with negative cosmological constant. Now the negative is a bit embarrassing since I was just previously telling you about how great it is that we have positive cosmological constant in our universe. That means this is not a theory of our universe. No one promised you a rose garden. Nonetheless, it is a toy model, and toy models are good. If you like, this is the simple harmonic oscillator of quantum gravity, this lambda less than 0. Now, this is the metric. Depending how much you look at metrics, this may or may not make sense to you. You can notice that there's this L here is a length scale. If this r is small compared to L, then this just becomes minus dt squared plus dr squared plus r squared d omega squared. This is some sphere metric. And that's just Minkowski space in polar coordinates. Okay, so this is some geometry that, at small r looks like ordinary Minkowski space, but then at large r it does something different. What does it do? Well, intuitively, I keep forgetting to take this joke out. See, I gave this talk to a Boston audience, and then this was really cool. I can't remember. Okay. So in any event, so what it's like living in anti-de Sitter space is, you have something and you throw it away from you, and then after a while it comes back. You see it move away from you, and then after a time, which is of order this L here, it turns around and comes back to you. And even if it's a photon, it does that. So it's life in a box. It's gravity in a box. It's a closed system. You might think that it has a finite energy, it has a finite entropy as a function of energy, and you can study it as a closed Hamiltonian system. And that's what's great. It sort of keeps to itself. It doesn't get involved in the rest of string theory. So diagrammatically, it looks like this. So this r direction is sort of the radial direction here. Just t goes up and the angle is like this. So it's like living inside of a tin can. And maybe you're here and you shoot a photon. As usual, photons go on 45-degree lines. At some finite time, it gets to the boundary. Well, finite time from your point of view, of course, 0 time from its point of view. Bounces off and comes back to you, and this time here is of order this L. Okay, so that's life in anti-de Sitter space. Now, an asymptotically anti-de Sitter space is just one that could differ from this at finite r, but which approaches this geometry at large r. And we clearly want that. If the only thing we described was empty ADS space, that would be a rather boring theory. That would be a theory with no excited states. It would be a one-dimensional Hilbert space, which, there's only so much fun you can have in a one-dimensional Hilbert space. What we want to do is be able to put stuff inside. So maybe here's us here, and then now it's gravity, so the geometry will change a little around us, but then it'll go back to ADS at large distances. Now, an essential point here is that as r goes to infinity, in any asymptotically ADS geometry, the metric, the induced metric on the boundary here, on the boundary of the can, just becomes a round sphere times time, okay, a cylinder. So, okay, as sd minus 1 times r. That's how a mathematician would write it. That's fairly obvious from here, right? Here's the dt squared, and here's the omega squared. Okay. So then, Maldaceno's proposal is that the quantum gravity theory of this family of spacetimes is defined as the conformal field theory living on this boundary. Defined. And so the definition is through some dictionary. So first of all, the Hilbert spaces are equivalent or isomorphic, if you like. Every state in the CFT has a bulk interpretation and vice versa. The Hamiltonians are the same, same energy eigenvalues. It's a discrete spectrum because it's a system in a box. And the other generators of the ADS symmetries also match. The states fall into the same representations of the symmetry group on both sides. And moreover, the thing which is essential for me, the thing which I'm going to get all the mileage out of in the remaining half hour of this talk, is that for any bulk field, phi, living somewhere in the bulk, as we pull it towards the boundary, so you see here's a bulk field, and I'm taking r to infinity, there's some scaling factor here, r to the delta, and then I get a local operator in the CFT. So this is sometimes called the extrapolate dictionary. I guess Douglas Stanford and I made up that name, but people seem to use it now. So this is how you make a sort of more concrete connection between the two theories. So here's the extrapolate dictionary in action. We'll look at some scattering amplitude in the bulk. So we can do that by acting with the bulk field, say here and here, and then acting with another one here and here, and computing a time-ordered correlation function in the bulk. And then since states go to states, well, I didn't write them here, but the ground state in the bulk goes to the ground state in the CFT. These phi's become O's, and then this thing is just some 4-point function in a conformal field theory, which is the kind of thing that any quantum field theorist sits around and computes all day. So in particular, note that locality of bulk operators near the edge just follows from this dictionary. Okay, so bulk operators near the boundary are going to be local in the t and omega directions, just directly from the dictionary. Okay, so that roughly ends the review part of the talk. That was just to bring everyone up to speed, make sure we're all at least somewhat happy. So now I'm going to start talking about stuff which is more directly my own work. So you probably know that in quantum field theory, what I mean by locality or causality, basically the same thing, is that operators, local operators, commute as operators at space-like separation. So I guess this is space-like separation in the correct metric sign convention. Now, maybe just to emphasize, right, the reason why causality and locality are the same, right, is in quantum mechanics, if you have two operators and they don't commute, then the probability distribution for one of them depends on whether or not you measure the other one. Okay? So that's a telephone, because if I have these two space-like separated operators and I do or don't measure this one, I can change what you get over in the Andromeda galaxy. That's bad. Okay, so in quantum field theory, this is the mechanism that enforces locality is the mechanism that enforces causality. Now, we can think about this in the bulk too. Okay, so let's think about this kind of situation here. So here O of x is some, so here I take a fixed time slice in the bulk. This thing here is a t equals 0 cut through the bulk. And now I'm going to look at some bulk operator.
T is an arbitrary coordinate.
You're worried about diffeomorphism variance. Yeah, that's right. So I just take some space-like surface through the bulk whose boundary is a given t equals 0 Cauchy surface on the boundary. It can be any space-like slice. That's right. The time at the boundary is well defined because the boundary conditions are like impose a natural set of coordinates at infinity, and that's enough to make the statement.
So you're assuming that space-like is well defined in the bulk, which means...
That's correct, and well, right, and so that's going to be something we're going to comment on. So it's not in general well defined. If the geometry is fluctuating a lot, that's your worry. Correct. No, don't worry. Actually, I should drop. Okay, let me make an editorial comment now. The paradox. I said a paradox. I didn't tell you what it is yet. The paradox I'm presenting here is the 0th order version of a paradox, which needs to be improved to deal with what you just said. Now, it can be improved. I know how to do it. But I think it would take us a little bit too far afield for me to say in detail. So, but I'll comment on it a little bit more in a second.
Okay.
Okay. Now, so for now, I'll just say I have some bulk operator here that's a local bulk operator in the center of the bulk. And it's space-like separated from all local operators on the boundary of this slice, okay? Because it's a spatial slice. Now, in the bulk, they're space-like separated, so given the rant I just gave here, you might guess that they should commute. Now, there's a subtlety, which was just alluded to, which I'll very briefly comment on, which is that in a diffeomorphism invariant theory, local operators don't make sense. True fact, this is really a non-local operator. I have to define its location in some gauge invariant way. There's a grown-up version of the paradox I'm about to say, which takes that into account, and the conclusion doesn't change. Okay, now, in the CFT, remember that operators in the bulk, right, correspond to operators in the boundary theory. The Hilbert spaces are isomorphic. Okay, so we might think that in the CFT, if phi of x is an observable that makes sense, there should be some phi of x operator in the CFT, and there will certainly be some O of x operator, because that's just some local operator on the slice here in the CFT. And so you might guess that bulk causality tells you that these guys need to commute. That's impossible. In quantum field theory, any operator that commutes with all local operators at a fixed time must be proportional to the identity. It must be a C number. Here's a statement. Let me make 2 comments to justify it. By physicist standards, this is a theorem of local quantum field theory. By mathematician standards, this is called the time slice axiom. You can read about it in Streeter and Whiteman, or in Haag. It's been proven to be true in various special cases for the usual reasons that it's hard to prove anything in local quantum field theory. I can give you some intuition, however, for why you should expect this to be true. The reason is that the set of local operators at a fixed time act irreducibly in the Hilbert space of a quantum field theory. So, for example, if you think about some scalar field theory, there's a complete basis of states which are labeled by spatial field configurations of phi of x at a fixed time. By acting with e to the I integral dx of p of x, which is a local operator, it's the momentum conjugate to phi, integrated against some function of our choice, we can get to another element of this basis, and in fact to any element of this basis, which means that the algebra of local operators indeed acts irreducibly on the Hilbert space. Now, as you may remember, there's this thing called Schur's lemma, which says that any time you have an irreducible representation of an algebra acting on Hilbert space, a bounded operator that commutes with all elements of the algebra must be proportional to a C number. Okay, so that's why you think this should be true. That's therefore why this can't be true. And thus what we've learned is that the algebra of operators that we might expect in the bulk theory cannot be realized in a CFT at the level of the operator algebra. So locality, causality, which in quantum field theory is an operator equation. It says the commutator of O of x and O of y is 0. cannot be an operator equation in the CFT.
But you have to have some conditions on alpha, right? Because alpha doesn't, is that alpha up there in the ground?
Yeah.
If that doesn't go to zero fast enough in infinity, then there are problems just
That's right. So that has to do with defining what you call the Hilbert space of the
exactly.
quantum field theory. So in this case, first of all, the field theory that I'm studying is on a sphere, so there is no infinity. So the IR is fine. You could still complain about if this alpha is not sufficiently smooth, that there might be issues with infinite energy states. But let's just, for example, say that alpha, just to be crude, let's just say alpha is a C infinity function, and then the Hilbert space I span by C infinity functions on the sphere. Maps from the sphere to the real line. Yeah. Okay. In the remainder, so that's a paradox. I think this is a correct argument. Now the question is, what are we to make of this, right? Because I just argued that locality can't be true in the usual sense in ABS CFT, but it seems pretty damn true that locality is here in this room. Okay, and we have quantum gravity here, and causality seems to be respected, locality seems to be respected, and so we better understand why that's true in ABS CFT, even though we have this, even though we can't have this.
Why do you know that about this room?
What?
Why do you know about this room? That locality is expected. So
well,
really this is...
Well, so it's true in some sense, right? I mean, it's true. So at the LHC, when they test the standard model, they do quantum field theory calculations.
Really, what do you know? Really, is not locality, but asymptotic commutativity. That's really what is important. That if you have large distance between operators, they almost commute. It is not necessary.
Well, that's related to what I was saying before about the S matrix, right? So I think so. I will insist that no particle physicist, however much the textbooks say contrary, actually measures an S matrix, because an S matrix is at infinity, right? What we actually do is we have wave packets that are sort of reasonably localized, and we collide them, and we have detectors that are a certain position, and we measure time-ordered correlation functions.
You do not have local operators.
Yeah, but they're roughly local. I mean, the CMS detector is fairly local in the end.
That's not needed.
Yeah.
Roughly
That's
local.
right. So right, roughly local. So that's why I said it seems to be pretty true. We can negotiate how true. I would say that I would go further though. I would say the fact that the standard model is confirmed in the LHC up to scales of order the mass of the Higgs boson, I would view as evidence that locality holds even down to those scales. Now you could contest that, and you could say that we're not actually directly measuring correlation functions at that scale. I don't really buy that. That's like saying that electrons don't exist because I never see electrons. Have you ever seen an electron? No. I mean we do indirect experiments based on assumptions, and then we see if the results of the experiment are consistent with those assumptions, and then if they are, we take it as evidence for the assumptions. Okay, sorry, that was maybe a bit of a distraction. Okay. Now, in the remainder of this talk, I'm going to try and convey some flavor of a resolution of this paradox that I recently proposed, together with Ahmed Almiri and Shidong. So Almiri is the A from AMPS, so he's one of the hooligans. It's also a beautiful human being. So what I'll do is I'll first relate this question, this commentator question, to a seemingly unrelated question in the ADS-CFT, which is the validity of something called subregion duality. I will then argue that a formalism called quantum error correction, which was developed really first by people who are trying to make quantum computers, actually is beautifully suited to thinking about both the problem I just described and the subregion duality. And it gives you a natural way of thinking about how to resolve this kind of paradox. And finally, I'll return to the problem that I started with, which is how is the possibility of forming a black hole disrupt the emergence of locality? And I'm going to argue that quantum error correction gives us a nice way to think about this. Now, in ADS-CFT, there's actually a semi-standard prescription for representing local bulk operators, like this phi of 0 in the center, as operators in the conformal field theory. So here's some list of names which is associated with doing this. You write a formula that looks like this. You say that phi of x, where x is some point in the bulk here, say that one, is really some integral over a region R, which I've shaded green on the boundary here, of some local operator O of x in the boundary theory, which is the same O that appears in the extrapolate dictionary for phi, against some kernel, which is called the smearing function. And then there are perturbative corrections to this formula that you know how to compute. The details of this don't really matter very much. I just want to emphasize that this formula exists. And this is called global reconstruction. Why is it called global reconstruction? The reason is that if I think about everything at a fixed time in the boundary theory, so say on this boundary Cauchy surface here, I can write this operator in terms of Schrödinger picture operators at a fixed time here, but it will be a very non-local operator. So because what I do is, so this O, right, this R has non-trivial extent in time. So to take a Heisenberg picture field up here and represent it as a Schrödinger picture operator at time t equals 0 is a big mess. You have to formally solve the Heisenberg equations of motion at the level of operator equations, and you'll get some big non-local mess when you do that. And in particular, the non-local mess will have support all over this entire time slice in the CFT. So it's called a global representation of the operator. Now, in fact, there's also a more subtle way of doing this, which is called ADS-Rindler reconstruction, which allows you to get a representation of the operator just on a subregion of the boundary, and not over the entire boundary. So you write a similar formula. This K is different now, but the point is that now, so here's some subregion A, and then the idea is that for any subregion A at a fixed time, you can define some bulk region, which here is called the causal wedge A. And I've sketched the region here. It's roughly this piece of cheese. And then for any x which is inside of this region, there's a representation like this, but where now the operator is integrated just over this diamond, which is the boundary of the wedge. And the reason that's good is now if I do this crazy Heisenberg evolution all to a fixed time, well, I only have to worry about operators that are inside this diamond, and since in quantum field theory everything propagates within the light cone, including Heisenberg operators, then the representation I get will only be non-trivial on A. Now, from the bulk point of view, these two different reconstructions, the Rindler reconstruction onto some region A, and the global reconstruction onto the whole thing, are going to give you the same operator because they're related by what's called a Bogoliubov transformation. If you've not heard of a Bogoliubov transformation, you can just ignore that statement, except, believe me, they're the same. Now, so here's a top-down picture. This is kind of confusing. If I actually define this region, I'd have to say a bunch of relativist gobbledygook about domains of dependence and intersections of various causally defined sets. The picture from the top is easier to understand. So this here is now just this slice, looking at it from above. Here's this operator phi of x, here's A, and then the idea is any x who's in this red region here, I can represent in the boundary theory on A. But any y over here, which is outside of the red region, is not representable on A. And then this dividing line between them is, in this case, going to be a geodesic, a spatial geodesic. Although that's actually a coincidence. It has some other definition that's more general. Okay, so just remember this picture, and you can forget the rest I said about the operator, about subregion reconstruction. So the reason this is called subregion duality, which I mentioned before, is that you have some subregion of the bulk, and things that are in that subregion can be defined on some subregion as operators in some subregion of the boundary. Okay. Now we can connect this to the commutator paradox I mentioned before. So say O of x is your favorite local operator on the boundary. I don't know. Let's say it's Albert's favorite local operator, and let's say maybe it's here. And here's phi of x, boxed in again. So I can just pick a causal wedge like that, right? I can pick A to be this boundary of this whole thing, where I drill a little hole around O of x. And now phi of x is going to have an operator representation just on the boundary of this red region. And every point on the boundary of this red region is space-like separated from O of x in the CFT, which means they commute. Okay? This red ADS-Rindler reconstruction of phi commutes with O of x exactly as an operator equation, no buts about it. Similarly, if I don't know, Marcus's favorite operator was over here, then I could have picked this ADS-Rindler representation of phi of x, and now this one commutes with this O of x exactly as an operator equation. And now clearly I can do that for any point on the boundary on this time slice. So if all these different reconstructions are equal as operators, then I'm again going to run into trouble with the time slice axiom / theorem that I described a couple minutes ago. This is what I said. You can always find a wedge for phi such that the commutator is 0. Now, this can only be possible, like I said, if the different representations aren't actually equal as operators. They're only equal in some sense, which is enough to explain their apparent equality in the bulk. Now, one final illustration, then I'll start telling you about the resolution. Okay, now I split the boundary into 3 regions, A, B, and C. Think about the operator in the center. This operator is not in the causal wedge for A, nor for B, nor for C. But it is in the causal wedge of A union B, or B union C, or A union C. So where's the information about the operator? It's not in any one of the regions, but it's in any 2 of them. It's a little weird. So something interesting is going on here. Okay. But what is it? What is it? All right, so now I'll tell you. So now, finally, we get to quantum error correction. And hopefully it will become obvious to you, as soon as I explain it, that that's what's going on here. So say I want to send you a quantum state in the mail. Some reason there's some state and I really want to send it to you. But we've been having budget cuts at the post office, and I'm not sure that it'll get to you, but I really want it to get to you. Well, if it were a classical state I wanted to send you, that's easy. I just send you 100 copies, and surely some of them will get through. And you can do, even if they all get through and some are polluted, you can do majority rule to figure out which one is which one is the right state. But as you know, there is a no cloning theorem of quantum mechanics, and so I can't do that. Again, I can't clone the state and just send it to you 100 times. Nonetheless, there is a way of encoding it, somewhat redundantly, and sending it to you, which protects it against this kind of corruption. And so that's quantum error correction. And obviously, it's a major part of doing quantum computation. In a quantum computer, your memory is always getting decohered, almost instantaneously, and you need some way to prevent that. And quantum error correction is the thing to do. Now, despite the no cloning theorem, the basic idea is still you want to put the state into a larger Hilbert space somehow, in some kind of redundancy. Now, there's a whole formal theory of this. There are beautiful theorems. We found more theorems. I'm just going to give you an example so that we can all just see, in the simplest case, how this works. So say I want to send you a single qubit state. So a single qubit, a 3-state Hilbert space, 0, 1, and 2. And this is some state in it. I guess I heard that mathematicians don't like drawing ket notation. Sorry. I think I would get confused if I tried to write it in different notations. So then the idea is that I want to send you this state, but the way I do it is that I encode it. I send you a different state, which is a state in the subspace, a state in the Hilbert space of 3 qubits instead of 1. So this is a 1 qubit state I want to send you, but instead of sending you 1, I send you 3. But I send you 3 prepared in this state where this I tilde is a basis for some particular subspace, a 3-dimensional subspace, of the 27-dimensional Hilbert space of 3 qubits. And that special subspace is called the code subspace. Now, why would I go to the trouble of doing that? Well, here's the subspace, just to pick one. So this is the subspace that I'll do. You see that it's a symmetric subspace between the three Q-trits. Permuting the three Q-trits doesn't take you out of the subspace. And also the states are very entangled, right? These are very non-product states. Now, the entanglement is special. It's helpful because it leads to the property that any state I prepare in this subspace, if you look at the reduced density matrix of any one of the Q-trits, it's maximally mixed. It's proportional to the identity, and that's independent of the state. So any one Q-trit has no information about the encoded state. And given that that's the case, you think that you might be able to recover the state from the other two, if any one of them doesn't know anything about it. In fact, that's true. Here's how you do it. So, okay, homework problem to find this U12, but it's some unitary acting on the first two Q-trits. And the reason I like this unitary is because if I act on one of these encoded, on one of these encoded basis states, well, what it does is it just pulls the I out and writes it on the first Q-trit, and then we get times some state on the second two where this chi is independent of I. Okay, so that's the homework problem. Find a U that does this. Well, why do we want that? Well, because now, so say I send, say I send Marcus this psi tilde. But say the third Q-trit gets left behind in the mail. That's lost in the post office, he only gets the first two. Well, he'll act with this U12 on the first two Q-trits that he got. And look, now he's got the state back on the first Q-trit. Times some, so he only has the second one, so times some maximally mixed density matrix, which he just throws out. So we can recover the state. And then remember, since this was symmetric between the three Q-trits, there's also going to be a U23 or a U13. So Marcus can recover the state from any two of the Q-trits. That should start sounding familiar to what I said before. We can make it more similar. So there, in the thing where I split the boundary into three parts, I was talking about an operator, and I wasn't talking about recovering a state. But we can easily do that too. So say O is some single Q-trit operator. So it's some operator in the three-dimensional Hilbert space of the Q-trit. So I can always find some three Q-trit operator O tilde that implements the same transformation on the protected subspace. But usually this O tilde will be some complicated operator. If I just pick some stupid subspace, not this subspace, then O tilde will act non-trivially on all three of the Q-trits in order to accomplish this. Here, however, we can use our U12 to define O12. So what does O12 do? Well, first it acts with U12 to map the state onto the first Q-trit. Then it acts with O just on the first Q-trit, and then it re-encodes it with U12 dagger. Okay. And this does the job. So this gives you an operator acting only on the first two Q-trits, which implements any operator of your choice on the protected three-dimensional subspace. Now, again, remember now, so it's symmetric, so there's going to be an O13 and an O23, and now you see we're exactly in this situation again that we had in ADS-CFT, right, where we had a phi of 0 here, which we could represent here, or here, or here. And you see now we've done that explicitly with the Q-trits. So, by using the entanglement of the code subspace, we can recover this sort of somewhat counterintuitive feature of ADS Rindle. We can also make contact with the commutator. So, for example, let's look at the commutator of O tilde with X3, where X3 is some operator on the third Q-trit. But I'm going to look at the matrix elements only between states in the code subspace. So this phi tilde and psi tilde are two states that are in this three-dimensional subspace. Well, then I can replace this O tilde acting to the left. It's acting on the code subspace, so I can replace it by O12. And acting on the right, I can also replace it by O12. And now it commutes with X3, because it's acting on the other two Q-trits. So then the commutator is 0. Similarly, if I had an operator X2 or X1 acting on any one of the other Q-trits, well, I could have done the other replacement, and it still would have commuted. So you see we've achieved that O tilde is commuting with all local operators. Now, there was a theorem that said we couldn't do that, and of course the theorem is correct. So what's going on here is that we have this restriction, that this phi and psi only get to be in a certain subspace. They don't get to be any state you want in the Hilbert space. And that's the lesson. The lesson is that in ADS-CFT, maybe what we should really want is that the bulk algebra of operators holds only on a subspace of states. Now, okay, that was just some toy model. Obviously, you can pursue this further. There's a whole general theory of error-correcting codes. And you can try and match, obviously the ADS-CFT isn't just going to be the 3 Q traits. We need a general theory of this. And we can try and match things that we know about that theory to things that we can understand in the bulk in ADS-CFT. Now, I don't have time to talk about this today, where I'm basically going to stop here. So I just want to mention a few of the highlights on the next slide or two. So first of all, this code has the property, the ADS-CFT, error-correcting code, has the property that quantum information located further from the boundary is better protected in the CFT. So for example, think about this operator in the center. And let's say that we erase this green region here in the boundary. It's a rather big region. Well, we can still do an ADS-Rindler reconstruction of this guy on the other side, okay? So that information, for example, whether or not I acted with that operator is protected from this large erasure, or from this one, or from this one, or from that one. It's a very well-protected piece of quantum information. Whereas this operator here is not very well protected. This tiny little red erasure here can kill it. So what this is doing is it's in a quantitative way illustrating lore about ADS-CFT, relating the radial direction and the renormalization group. Here we're seeing very explicitly that long range, or very, very big, long wavelength erasures are necessary to kill information at the center. Screwing around with the short wavelength physics will not delete this operator, whereas for operators near the boundary, UV erasures can kill them. Okay. We can also study the question of how large can the code subspace be. It can't be the whole Hilbert space, that was the point of the theorem, but we can ask in ADS-CFT, how large can it be? How many states can we realize the bulk algebra on? So it turns out, and there's a theorem you can use to convince yourself of this, that you can match the point where the code has to break in the bulk directly onto the point where you make a big black hole. So you start trying to act with more and more of these local operators and ask that they all still be protected and still have the usual algebra. And right when you get to the point where the CFT is about to give up and it's about to say, no, you made the code subspace too big and I can't do it anymore, these are going to have to stop commuting, that's exactly the point where the bulk tells you that you should stop taking local effective field theory seriously for these operators, that because you've created a gigantic black hole and that the entropy is no longer growing like the volume. So that's nice. That sort of returns back to where we started the talk with. Any attempt to probe locality, to realize the local structure of space-time in quantum gravity theory, ADS-CFT, does break down explicitly due to black hole formation. Okay, now there are many things still we could ask about. I'll just mention one and then I'll stop. So far, what I've really done is I've given a proposal for how bulk locality is realized in the CFT. If you like, it's a cartoon, and I've done bulk calculations and seen that they're consistent with the cartoon. But can we really check it in detail? Can we really see directly in the CFT that all of the necessary and sufficient conditions of the quantum error correction theorems are really satisfied? In the CFT, that's a little bit too hard. What we can do, however, is we can look at toy models. Go even further. Even more toy models. So together with Fernando Pestovsky, John Preskill, and Ben Yoshida, who are all from Caltech, I've been working on developing an explicit model, of the error-correcting code, a discrete error-correcting code. It's called a stabilizer code, if anyone here knows about coding. Using methods from condensed matter physics and quantum information theory, which are called tensor networks. It's the upshot is that they do realize everything that I said here in a nice and sort of provable way. It's amusing that these are actually generalizations of the codes that people usually use in doing quantum computer algorithms, and they might be better, I don't know. If they are, though, I would certainly enjoy that. That would be an engineering application of quantum gravity. 20 years from now, when you've got your quantum computer in your phone in your pocket, might be the way it might be protecting itself from decoherence is by simulating ADS-CFT. So I think I'll close with that. I'll just show you a picture of what these things look like. That's what they look like. They're fun to think about. Okay, thanks.
Questions? All questions were answered? Yes.
The picture of the space slice where you were saying that some states are more protected than others.
Here?
Yeah, that one. Have you thought about notions of coexistence? when
Yes,
you're
that's
thinking
right.
about this, and making like thinking about quantum metric sort of space.
That's right. So in the CFT, it's hard to quantify that, but in these models, you can try and prove a threshold, which is basically roughly that. It's a little bit weaker than the distance, but it's a sort of statistical distance, and that you can prove. So you can prove that this code has a threshold which is order 1. So you can erase some finite fraction of these, and you can still reconstruct the guidance.
Yeah, yeah.
Yeah.
Do I understand correctly that this means, in a sense, that there is no locality at the operator level, but only at the state level?
That's correct. Yeah. So locality is a statement about the operator algebra acting only on certain subspaces of states. Yeah. So you have to put the states in. It's not just an algebraic property.
Okay, so we're going to have a discussion tomorrow, and I've forgotten the time, but I sent out an email on that. When is it again? I think it's a slightly unusual time.